Okay, so I'm going to talk today about one of the research directions we've been working on in my group, which basically is focusing on developing digital twins for optimization of underground storage operations. And since there's a lot of uncertainty in the Earth subsurface, we make it uncertainty aware. And there's also context, which basically means that there could be different physical processes active in the Earth. And so depending on the context, the digital twin will behave sort of differently. Now, this is really work that's done by my graduate students that are listed here. Some of them are finished, some are about to finish. And it's done as part of the Seismic Laboratory for Imaging and Modeling at Georgia Tech, where I also run the MO for Seismic Center. Okay, so what are we up to? All right, so so there's basically a need for CO2 monitoring. We feature it a little bit less prominently given the current political climate, but that was one of the main, but not only drivers of doing this, where you inject CO2 in the subsurface and you want to monitor what's going on and you want to control what's going on. And then, of course, there are other things. You can do hydrogen storage, which is basically a similar problem. And so what I'm talking about is quite generic. It could also apply to the good old dirty oil and gas production. So okay, so what's the challenge here, right? So we don't know really what the permeability is, right? The permeability is the ability of rock to allow for fluid flow, and we have multi-phase flow. So in case of geological carbon storage, we have brine, which is saline water, and we have CO2, a mixture in porous rock. But we don't know what the permeability distribution is. That's the spatial distribution of the permeability, right? And so you see here at the bottom two realizations of the permeability field that we derive from seismic, and I'll talk about that later. And superimposed on it, you see a plume. And you can see that for two realizations of the posterior for the permeability conditioned on seismic data, you have quite a different behavior for the plume, right? So in this case, after the first time step, it almost already protrudes all the way through a high permeability zone to the edge of the box. And this box is basically a legal entity within which the operations have to take place. And so that's a problem. Right, so the challenges really in underground storage is manifold. Aside from that we don't know much about the subsurface, things are also typically computationally expensive, right? They're high dimensionals, there are many degrees of freedom. It involves nonlinear multiphysics, not only multi-phase flow that describes how a injected CO2 plume behaves over time in the subsurface, but also seismic wave propagation, because we use seismic waves to basically monitor the plume, right? And so now, given that we don't know what these fluid flow properties are, we need to basically deal with this on a fundamental level, how these reservoir fluid flow properties behave, because they are responsible for the dynamics. That is, how does the plume develop over time as you inject, and even also after post-injection, right? Now, with a lot of these things, we cannot run risk, right? There's H2. If you get an H2 cloud out there, that's highly explosive. Also, if you injected a lot of CO2 at high costs, you don't want that CO2 to come out. And so we feel that we have to do basically a principled way of doing uncertainty quantification that will then inform basically how we run operations and how we optimize operations. Now, we will use machine learning techniques to capture these very high dimensional distributions, but these are delicate. And so I will talk about today how you can make these approaches more robust with respect to statistical misspecification, right? Where you may not capture everything in your simulator, there may be noise or your prior may be wrong. And so in that way, we hope to avoid biases or even wrong predictions for the posterior samples. So today I will make our digital shadow, which I explain later what that is, into a twin, and I will make it more robust with respect to incorrect simulations. That's really the context. And then I will talk about how we can optimize operations. So I'm not going to read the definition, but I find it's one of the best definitions for digital twin. And so that's what we do. And I come later back to this in a little bit more detail. And we try to build an open source platform that supports everything I talk about today. So the first step is that we need to establish a probabilistic baseline. That is, at time 0, we need to basically do a seismic survey and try to figure out what goes on in the Earth. And for that, we use a full waveform inference technique. And that is published in this paper. And the software that goes with all these things is for this part is here. And there's also software for the twin I will point to later. So what are we looking at? Right here we have an example of a gridded function of the Earth properties that is derived from wells and seismic. So you can see there's a lot of heterogeneity. And then there's here a reservoir rock that's a saline aquifer. So that's a sandstone that has a reasonable permeability, but the permeability is not homogeneous. And so you can see that this plume, as it develops, follows the high permeability streaks. And we simulate this by using a reservoir simulator that basically describes how supercritical CO2 that's being injected propagates and pushes out the brine that sits in the rock in favor of the CO2 come. And so, well, what do we need to do in order to establish this baseline is to use seismic techniques. And for the seismologists amongst you, you will recognize this. For those of you who are not seismologists, this is like a seismic image, but it's a common image gathered, so it's sort of redundant. It has an additional coordinate, which is a little bit beyond the topic of today. But that is something that's a physics-based technique we can apply to the seismic data we collect at the surface and bring it into the image space, and can use that as a condition for a conditional distribution, which is the posterior distribution, that gives you realizations of the velocity model. And that's a gridded function for the wave speed as a functional space. So this is the subsurface. At the top here, you see water, and then you see color-encoded different wave speeds. And what you see as the movie goes, different realizations of the posterior, all conditioned on the same observed seismic data. Okay, and so that gives us a baseline. So here you see the movie basically in a 3D stack. So you see one slice in the middle, and then you see all the different slices, which are different realizations of the posterior for the velocity. You can see there's quite a lot of variation amongst them, which reflects the uncertainty that we have in the seismic properties. Now we make a little bit of leap of faith here, and we try to associate these changes in the acoustic wave speed to changes in the permeability. And we do a one-to-one, but a stochastic sort of mapping, where we do a very important element-wise relation, so that we can actually form basically realizations of the permeability field. So kappa here stands for the permeability field, and we can randomly sample from it, basically through samples of the posterior for the baseline for the seismic. Right, and so these are basically samples of the permeability model that reflect our lack of knowledge of the permeability field in the subsurface. And so everything we do is based on the open source packages. We use utool, which is a Julia package that can do battery simulations, but also the Darcy equation, and that's relevant for multi-phase flow. And we use for seismic DeVito, which is an open source just-in-time compiler for finite difference stencil-based calculations for the wave equation. And then we have a linear inversion framework based on top of that, which is called Judy. It's not linear, it's just an inversion framework. And so, and we do then, we simulate 4 time-lapse surveys with every 480 days, and these are some specifications on the type of acquisition we have, and we solve the full nonlinear wave equation and then image it. So there's a nonlinear map between the state of the reservoir, which are the saturations and the pressure within the reservoir, and how that's linked to say acoustic information, acoustic observations through the nonlinear wave equation. So let me go through the life cycle of the digital shadow. And so digital shadow is basically data assimilation without control. And so we call that a digital shadow, not a digital twin. And so it's based on dynamics, right? So X is the state, and the state is basically the pressure and the CO2 saturation. K is a time index. And then this calligraphic M represents basically a transition density that takes us from a previous time step to the next time step. That's dependent on a control parameter. That's the injectivity, Q. And there's a kappa, and that's the permeability, which is basically a very nonlinear noise term. So basically, every time when we apply the dynamics, we draw a different sample from the posterior distribution. And then we have indirect measurements, yk, through an observation operator, and there is noise. And so that's basically what we have. So this permeability is treated as a statistical nuisance variable. And that's basically sampled from the probabilistic baseline that I explained a minute ago. And then, of course, this H is not only seismic, but can also relate to measurements at wells. And so, and if I have time, I will talk about some experimental design optimization you can do for that. Okay, so let's consider this problem as a Bayesian filtering problem, where we are dealing with the transition density that's basically given by the M of the previous page that relates the state of the reservoir at time k minus 1 to time k. And then there is an observation density or conditional distribution, basically, that links the state to the observations, right? And so this first one is a Markovian transition probability that only depends on the previous time step. And then this second one can be thought of as a likelihood and that reflects the measurement model. So that could be seismic or could be just direct measurements of wells. Okay, so how then to proceed is you can come up with a statistical inference technique. And that is basically a fundamental framework under which also Kalman filtering, all these techniques fall. And that typically contains of 3 steps to get to the posterior. That is, how can you get the state at time area k conditioned on all the observations from 1 to k, right? And so this involves an initialization where you sample from the original state. So for instance, you start injection at a particular position and a particular rate, and then you have to compute the predictive distribution through this integral, which links the state at the previous from 1 to the previous time step to the current state, and then you apply Bayes' theorem to basically get you to the current time rather than the previous time. Now, this involves high-dimensional integrations. That's problematic, but the nice thing is that this can be interpreted in the sense of Bayes. So this pyk given xk acts as a likelihood, and you have a prior, but the prior really has information of the past of the system. And so the marginalization over this xk, but actually also over the permeability, which is that nuisance parameter, is unfeasible, right? So we have to come up with a technique to overcome that. So let's first show in pictures what we do, and then I will go a little bit more into what the different steps entail. So here we have, and we look at the first time step. So at time step 0, we start injecting. You can see that the location at which we inject varies vertically, and the injection rate changes. Right, and then we apply the dynamics, right? And so that brings us from time step k minus 1 to k. Hat means it's saw basically observed data. That's a bit of a misnomer for k is 1, but for later iterations you will understand what I mean. So what we do now, we draw different samples for the permeability model and run for these different initial conditions, the CO2 multi-phase flow simulations. And here you see the CO2 saturation, right? Then we use rock physics to translate these to changes in the seismic properties. We generate seismic data and we make an image. That's encoded in this operator H. And you can see here seismic images that are very noisy. And you can see that they have basically varying plumes, and that's the imprint of this saturation. So these two are basically can be considered as samples of the joint distribution for both the state at time k and the observations at yk. All of this is basically simulated, right? And so we use a technique from simulation-based inference to train on this ensemble a neural network, right? And that neural network is basically trained to approximate the posterior distribution that gives you samples of the posterior xk given yk, right? And that approximates the posterior. And this phi hat is basically, these are the optimized network rates that we trained while basically working with this ensemble. Okay, so if you have this, then if field observations come in, so this is, while simulated, it really needs to come from the field, then we can condition basically the forecast onto the analyzed state, right? So the forecast is here, and then the analyzed state maps basically the forecast that used the dynamics alone, and then uses the observations to do basically a posterior inference. So that's a mapping, basically prior to posterior mapping, right? And then we recurse. And so we go then into the next step. Now, of course, these guys have seen observed data. That's why we have the hat here. Okay, and that is a digital shadow where we map the simulated state xk to the conditions on field data xk hat, right? Given observations from the field. Okay, so let's make this workflow work on an example, but it's all simulated because we don't have field data that basically allows us to do this. And these injection projects, they take many years, so we don't have that. So we simulated it, right? And so here is the ground truth, and that's something we haven't seen. And so the only thing we will see here is measurements at wells and seismic, nothing else. But here we show what's going on. So there's a plume here in a permeability model that induces time-lapse changes in the wave speed and in the density, which are the two properties that the wave equation are sensitive to because they appear as coefficients in the wave equation, right? And so these changes we can then observe seismically, right? And so, okay. Now, this is a bit too busy, and I'm not going to go over all the details, but I just want to tell you we use a full nonlinear forward operator to solve, basically to map the densities and velocities at different time steps to data at different time steps. And then you use a cleverly designed imaging procedure that maps all these things back to the image space. And I refer to our paper to how this really works. It's a little bit too much detail for this presentation. But the idea is that we take data and map it back to images of the time-lapse differences, and that are the differences in the plume that are induced to flow and injection of CO2. And so we really work with very noisy data. So this is the difference between two surveys, I think between time step 1 and time step 2. And this is for the first, second, third, and fourth, so the 4 time steps. And you see here, if you have good eyes, you see some difference developing. And that's basically for one, we see one source. We have many sources firing because we do an active source seismic acquisition. We see basically a different time-lapse data. And this is what is being mapped to the image space that gives you an image of the activity. So you can see there's quite a lot of noise. Now, this is what we never see in the first 2 columns, except what we see at the well. So here we see basically for the 4 time steps, the plume developing. So you can see that the plume grows because over time we inject more and more CO2 and the CO2 flows out according to these multi-flow phase flow simulations. And then we see the pressures. So this is a pressure perturbation because if you inject CO2, you raise the pressure, and that typically propagates out much faster and carries danger, because if you inject too fast and you raise the pressure too much, you may break the rock. I'll talk about more of that later. And here you see the imprint of the plume over different time steps. So what we have is basically the data here on the right. We have that. And we have the data at the wells, but nothing else. Okay, and so here you can see again what happens. We see a fine-grained simulations of the plume. So we see 24 time steps, and then every 6 time steps, you can see that we take a survey in the field, and you can see then the plume growing. And this is what we see, including what we see at these 2 well locations. Okay. So, okay, so we have to train these networks on the ensemble. The ensemble is quite similar to an ensemble in an ensemble Kalman filtering, but a couple of important differences. First, everything we do is highly nonlinear. Second, we have that nuisance parameter, the permeability, that appears nonlinearly in the dynamics, and that breaks ensemble Kalman filters. We couldn't get ensemble Kalman filters to work. And so, okay, so we do the dynamics. So we have to solve a mass balance equation and Darcy's equation. Again, we use this work by UTool, which is by Olaf Moyner, who is a big shot in multi-phase flow simulations and built an open source simulator that solves basically Newton-Raphson iterations to get to the state. And the state, again, in our case, is the pressure and the saturation. And here you can see again an instance where we start at time 0. We draw for every ensemble member a different permeability, and that gives rise to this greatly varying plumes. So that's basically the forecast for the state. And then of course there's also pressure. And then we translate these to simulated seismic. So we see on the right simulated seismic. We see here at the bottom simulated pressure, and here on the top the saturations. And here on the right you see the pressure that we measure at two well locations. Okay, so we can use this now to train a network, right? And so there are many different generative models that and basically that capture conditional distributions, and we use basically normalizing flows. And they can be basically thought of as a parameterization for the conditional distribution. That's conditioned on y, and it gives you x. So y again is the seismic image or the well data, data collected at the wells, and x is the state. And so we basically want to approximate the true posterior distribution, and we're doing that by minimizing the KL divergence between the true posterior distribution and the approximate one, which you can rewrite in terms of a maximization of a likelihood where we have access to samples of XY, right? And we have actually samples, access to samples of XY. And so then we can train that neural network by having these samples, right? And so we can sample from the joint distribution, as I described when I went over the life cycle of the digital shadow. Because we have access to samples of the transition density that's given by applying the dynamics. And those are basically can be seen as samples of the prior. And then we can generate seismic observations, and they produce samples of the likelihood. Hence, we have samples of the joint distribution. And we can give those to a normalizing flow where the network is learning to turn xk conditioned on yk into white noise. And so this is basically an invertible neural network where we train the network parameters like so. And then you have to have a log-dat term that takes care of that you changes in volume because you do a nonlinear coordinate transformation. Anyway, you can solve this and quite effectively. We only need m, which is the number of ensemble pairs, like order 100. Not 1,000, order of 100. So it's certainly doable. The cool thing is when you do this training, you marginalize over xk as well as over kappa. So you deal with these untangible integrals that I showed earlier. Okay, so what do you do during analysis? You're basically doing this forecast to analysis step mapping, right? And so this is called the prior to posterior mapping. That's also fundamental to an ensemble Kalman filter, right? Where the mth member of the ensemble at time k is linked to a basically to xk, that is the forecast, and the yk, right? And so in the end, you can write this thing in terms of the covariances for the ensemble and the of xy cross covariance and the autocovariance of y, and then you condition on you use the observed y. Okay, now this is delicate. We couldn't get it to work because it assumes the linear or almost linear forward maps, and it cannot really handle very complicated noise terms or nuisance parameters. So we do something else, and there are two options. You have either reference to conditional or join to conditional. The reference to conditional assumes that the normalizing flow is perfectly trained, but it means it will turn, conditioned on the observed data, a realization of white noise into a sample by running the network in the inverse direction, and that can be done because it's an invertible network, and that gives you samples of the posterior conditioned on Y. Or you can do something more clever, and that was an idea that was independently proposed by Marzouk, and that is a coupling technique where you have basically a triangular transport, where you map basically your ensemble for each M to the latent space, and then you go back with that latent space conditioned on the observed data. And so that's like a triangular mapping, that's more robust. Okay, so let's go over this. So here we have again the observed data, and then we can go basically to the plume predictions. That's just applying the dynamics to go to the next state. Then we condition on the observed data, we get these. This is the conditional mean, and that's the conditional mean for the prediction, so you can see you improve dramatically. And so here you can see the ground truth on the top left. If you use information at the wells only on the top right, if you use seismic only at the bottom left, if you will use well and seismic on the bottom right. And this is really a slide that should tell that reservoir engineers and seismic people should talk, because the combination works the best. And you can see here, this is at the last time step. If we can also look at the standard deviations on the left and amongst the posterior samples on the right, sorry, and on the left, the error, they should sort of correlate, and they do. And you can see that we have a reasonable estimate for the uncertainties that correlates well with the errors that we know in this case. Okay, so that was all digital shadow. Now, let me use the last 15 or 16 minutes to talk about a digital twin, right? So we did a lot of things here in green, but what we didn't do is reasoning and decision making, right? And so why do we need to make decisions? Because we lack robustness with respect to misclassification of the likelihood. So, for instance, we use a rock physics model to translate the saturations and pressures to seismic properties, and that may be wrong, right? And that leads to misclassification. And we haven't optimized operations either, right? So how do we get this? I cannot go back. Oh, here we go. Yeah. So the weakness is that we have fixed flow parameters in whatever we did, and we also have fixed rock physics that maps a change in the state, that is the pressure and the saturation, to a change in the wave speeds that can be observed seismically. And that's problematic because there are basically different rock physics models that link the saturation to the wave speed. And here, for one distribution in the saturation, you can see multiple seismic images when multiple different models are active. And they basically interpolate between a patchy or uniform distribution. And that has a big impact on that relationship. And we don't know what that relationship is, right? And so there's a lot of rock physics here. I have the equations. I can make these slides available. You can look at them. So it's not coming from nowhere. And that's a whole field in itself. But we introduced some red things, and those are unknown parameters, and they are going to be the context. And they determine how the saturations are distributed and how our properties depend on pressure. And so, and why do we do this? Because if you evaluate the digital twin on data that came from a different rock physics model, then the plume is not well recovered. This is the true plume on the left if we remain in distribution, but if you're out of distribution, things break. And that's because you asked the network too much. You didn't see the right relationships between the state and the seismic observations. So what we can do is we can, during training, vary the rock physics through a context. And the context is basically an additional parameter we train on. And then you can condition not only on observed YK, but also on C, right? And so we can ask questions, what do the posterior samples look like given a particular context? And you can do that by weight sharing. You can make the network conditional on this. And so you can basically handle the fact that you do not know the rock physics perfectly. And that can have a big effect. Here you see different instances of different dependencies. And this is the changes for the wave speed. And now you see in sort of pink, the changes induced by the pressure, and not only by the saturation in the middle, because the pressure has an effect on the wave speeds as well. And so that all becomes pretty complicated. So we can actually correct for this. And so we can do it with we can correct it. So even though we had the wrong physics, we can correct it by changing the context. And here you see the corrected pressures. Okay, so why do we care for the pressure? So basically, up to now, what we're able to do is allow for different context and can choose the context that basically minimizes the data misfit the best. And then we select that, and then we have confidence that what we have as samples for the pressure on the right are correct. And that will allow us to do control under uncertainty. So what we have now at a particular time step, we have samples of the posterior conditioned on the observations for the pressure, right? And so we have xk of delta p. This is a change in the pressure that we have that's conditioned on the observations at time k. And what we want to do now is choose a injectivity such that at the future time steps, we don't exceed a fracture pressure. And so that's a control problem, right? And so why do we want to do this? Because we know a depth-dependent curve that's basically a curve that describes the pressure at which the rock fractures, because you induce too much of a positive pressure change, you increase the pressure too much in the reservoir due to the injection of CO2, and you basically fracture the rock, and therefore fracture the seal, and then the CO2 can escape. And so we use, again, that we have samples of the permeability and we have samples of the state at the previous time step, so we can optimize at the previous time step basically what happens at the next time step by optimizing the injectivity. And so why do we do this control? So if you don't do control and you inject a lot, so you make a lot of money, you can see anywhere in red you exceeded the fracture pressure, and then you really have risk that you fracture the reservoir. On the right, there's a point of failure where we basically chose the injectivity in such a way that we are never exceeding the fracture pressure. But you can see now that we inject much less, right? And so you make less money. So how can we manage this somehow, right? And so and how do we do it? So what we're doing is we're trying to maximize how much CO2 we inject, right? But we want to at the same time ensure reservoir safety. And so the objective is that we want to maximize the injectivity as a function of time at discrete time steps. That this is really a sum, but I write it here as an integral, and that integrates this and that it should be maximum. So we inject the most amount of CO2 because I'm being paid by the number of tons of CO2 that I inject, right? And then I have constraints. Now you can do probability of failure or likelihood of exceedance, a pressure constraint, which basically controls the probability of any exceedance. So you cannot go epsilon over your fracture pressure. Or you have a conditional value at risk, CVAR, or that's also known as a superquantile, that controls the tail severity. That is, it tries to control the average exceedance, and so you have a control. You may transgress, but you can control by how much on average. And so this basically, the POF tells you how often failure happens and basically tells you to never have it, or if you introduce some epsilon with some rate, it's still very, very conservative, right? And it's unstable, and also it's non-convex. CVAR, on the other hand, you can control the severity of the tail, and that basically is robust and reduces the impact of rare extreme pressures. And so that gives you a smoother injection control. So a little bit more in mathematics. So the POF of epsilon is that epsilon is the percentage of pixels in the model where the fracture pressure is exceeded, right? That's epsilon. And the CVAR is the mean pressure over the largest alpha pressure cells that remain smaller than gamma. So you have basically look at the largest alpha fraction of pressure cells, and then you make sure that that remains smaller than some gamma. You can control those. And we do this all over 128 permeability samples that are related to the samples of the ensemble. So then you can do histograms. On the horizontal axis, you have the injectivity, and the vertical axis, how often do you basically fracture? And so you can make these histograms and you can fit them with some KDE. And so you can play with, allowing for some transgression, right? And you can see that then you move to the right. That's with the POF. And with the CFAR, you have two parameters. You have the gamma and you have the alpha. And the alpha plays a role similar to the epsilon. So you move to the right. To the right is good because you will inject more. So you make more money, but you may exceed, right? And so, okay, and so then we can do some statistics with bootstrapping, a lot of technical detail, but we can basically answer the question, can we make sure that the probability that we exceed the fracture pressure remains small? And we can do that either according to Q's that were calculated according to this constraint of the point of failure, or with the CFAR. And you can see that with the CFAR, we inject almost 3 times as much, which makes you make 3 times as much money, but you will exceed the fracture pressure sometimes, right? So here on the left you see POF, you never exceed. In the middle you see FAR, so you're slightly pink, so you exceed sometimes a little bit, not much. That's controlled, and on the right there's no control. And so why that matters is that you inject more. So if you have no control, you inject a lot, you see a very big plume, but you have a lot of fracture, pressure exceeding the fracture pressure, which you don't want. If you do a POF, you can control it, but you inject much less. Whereas if you do CFAR, you control your transgressions in a way, but you inject significantly more, right? Compare these two numbers. Okay, so yeah, that basically makes the point again. And so in the end, the bottom line then is if you look at time and you integrate the amount of volume that you inject over time, that is basically how much CO2 we capture from the atmosphere and store there for geologic time. So that's really why CCS is basically, or geological carbon storage, is considered as one of the few truly scalable net negative emission technologies. You can see that if you use the CFAR, you inject by far the most. If you do no control, you break the reservoir, so everything comes out. If you are very conservative, you inject much less. And so this is basically an optimization, not example of optimization, but under the uncertainties that come from the uncertainty aware digital twin, that gives you ensemble members that can be considered as samples of the posterior distribution that reflects the uncertainty on the state in the reservoir. So we can do other things. We can do experimental design. So we can basically ask the question, if we are allowed to drill a new monitoring well, so we can monitor, say, the pressure at different wells, where should we put the well so that we reduce uncertainty the most? Because if you reduce the uncertainty, then the decisions I just talked about can be made sharper, and most likely you can basically increase your injectivity because the variability and therefore the confidence that you have in the assessment of the state increases, and therefore you can make more favorable decisions, or more economically favorable decisions, and that remain, remain under control of risk. So what we can do here is you can try to maximize the information. And so this normalizing flow framework that we have lends itself very well to do things like expected information gain. And that basically allows you to find a W, which is a well density, which is basically a function that indicates areas with a high density where you should drill in order to reduce the uncertainty the most. And so I will skip the mathematics, but it follows very naturally And there's a paper on this. I may not have it what we did, but it basically you introduce this mask, but the mask depends. It's binary, so you have either a well or you don't. But it depends on a continuous density W. And that's the one we maximize over, in addition to the network itself. So you include this in the training, right? And when you go from one time step to the next time step, because you always are training on the state and the associated observations at each time step. So here you can sort of see what's going on. We have basically the different seismic, but also wells. And here you have this well density. And so that tells you over the support of the well, over the support of the plume, it tells you where to actually put something and where not to put. So there was a well here already in the middle. So of course there you know what's going on. There is no plume outside of this. So yeah, it doesn't make sense to put anything there because no CO2 yet. And so it makes sense to actually put one here. And that will reduce then the uncertainty the most, right? That's basically what this optimization tells you. So this tells you where to go and spend a couple of $1 million to do an additional monitoring well that then will allow you to reduce the uncertainty the most. And you can do this, say, every couple of years. And so over injection periods of 30 years, you can greatly reduce the uncertainty by choosing smart locations for the wells. And so here you see, after 4 time steps, you see basically the plume, and you see the locations of the wells it chose. And here you see the different monitoring. So we have 4 different monitoring steps. So every 4 times we can drill a well, and we compare basically the optimized well placement and then the errors that we make in the forecast of the plume versus if we were to place them randomly. And you can see there's a massive improvement in the RMSE because we optimized the well placement using this expected information gain. Okay, so this basically gets us to from a digital shadow where we just do data assimilation to a digital twin because we introduced well placement, we did injectivity optimization, and we also did context that fits somewhere in between. But we're really doing a lot of things that turn a digital shadow. That's a term introduced by Mark Ash, who wrote a big book on digital twins for SIAM, and we turn it into a digital twin. So that brings me to my conclusions. I think, and I hope I was able to convince you that using machine learning techniques that have very strong ties to ensemble methods, but use instead of a linear prior to posterior mapping, they train a neural network to do this, and that can then map the state, which is the saturation and pressure at the time step that is forecast to basically an estimation through a prior to posterior mapping by typo here, by using seismic and well data. And we have samples of the posterior, so we are uncertainty aware. So we have basically access to different samples, and we can then over the different samples run optimizations. So we can, for each sample and ensemble, choose optimal injection rates that then allow us to optimize operations. But before doing that, I showed that you can make the non-robustness of any machine learning technique more robust by conditioning during training on different rock physics. And so you can do, there are many options what you do there, but by enriching the data set in this way, you can make it basically robust with respect to the underlying model, and that makes you robust to some extent to misclassification. We could do optimization, and that allowed us to increase the injectivity and significantly, right? And this is really the bottom line. This is either how much profit you make as an operator or how much we as a society have to pay, right? So the more you can inject over the shorter time, the faster we can address climate change and the more economical these operations are. Now, of course, all of this applies to other types of subsurface operations that could be, oil and gas, traditional oil and gas, or it could be other type of storage, or maybe even things like geothermal. Yeah, that was my talk. I think I went 1 minute over. I think there are like 40 minutes for questions. Thank you.
Thank you, Felix. That was fabulous. Open it up for anyone's questions here. If you have a question, please put it in the chat, and I will manage that and pass those along to Felix. Because I had one just to kind of get started with.
Sure.
So the inclusion of like the neural net to replace the linear relationship. Have you looked at other architectures as well and see how those do?
Yeah, yeah, we're continuously doing that or many. So yeah, you can do. So we're big fans of flow matching, which are continuous normalizing flows.
Okay.
We like the invertibility because that allows you to do these triangular mappings, which is not so trivial to do if you were to use a diffusion model.
Yeah.
But we use diffusion model for other purposes. I work a lot on full waveform inference, which I brushed over at this talk, where we use combinations of these. I think the CO2 state is complex, but it's not super complex. That's the reason also we can deal with like only like 100 ensemble. But we could never get it to work for the nonlinear case, that is nonlinear seismic and having this crazy basically nuisance parameter. We could not get ensemble Kalman filtering to work. Under the linearized assumption and a static, basically no uncertainty under the probability, or much less uncertainty, we could get it to work, and we have a separate paper on that. Yeah, you can find that. Yeah, but we're constantly looking into other networks. Actually, my student showed me something yesterday. I think normalizing flows are still pretty good.
Okay, wonderful. Thank you. Any other questions from our attendees? If you have one, please just put it in the chat. All right. If there's no other questions, I'd like to thank you again, Felix, for a wonderful talk and being part of the webinar series. This will be posted on the SIAM YouTube page if you'd like to look through it again. And thank you so much, and we look forward to seeing you at the next webinar.
Sure, and feel free to reach out if you have questions.
Appreciate
All right,
it.
thanks for the
Thanks so much,
opportunity.
everyone. Bye.
Bye.